Welcome, everybody, to our first MathWorks mini-series session of 2026. Can't believe it's already March of 2026. Here at RoboNation, we're already one event into the year, having just completed our RoboBoat competition. As you can see here on the screen, we've got the word RoboSub up here, so we hope a number of our RoboSub community members have joined us today. This one will also be very interesting for those of you who will be competing at Robot X and bringing an AUV to the challenge. But all of this is possible because of one of our partners over at MathWorks, Abhishek Shankar, who has been working very diligently and very hard to make something really special possible for you guys, which is a virtual environment modeled after RoboSub, specifically after our pool out in Irvine that we have been participating in for the last few years and will be returning to in July. So this is just a fun and exciting opportunity for you guys to check out this virtual environment, learn how it works, learn how to get your vehicles and everything loaded into that system. We actually have been partnered with MathWorks for a number of years. In the last couple of years, they've been doing something really special with us, which is a MathWorks Simulation Award. And so that's something we also encourage you guys that are part of RoboSub, Robot X, and SUAS to pay special attention to during the mini series that we have throughout the springtime, because that's a really great opportunity for you guys to get your name out there more as a team, challenge yourself more, get some resume building opportunities, is to compete for those particular simulation awards. So without further ado, I'm going to pass it over to Abhishek, who is walked the walk of all of you guys. He's a former student, now works at MathWorks and is our liaison to one of our big time and long time sponsors over at MathWorks. But without further ado, I'll pass it to him to talk about this very exciting virtual environment.
Thank you, Alicia. And hello, all. I'm super glad to be here. This is something that we have been working on at the MathWorks for about 4 months now. We were able to build like a virtual environment for RoboSub. I'll get started with the presentation. The agenda for today is going to be a little bit of introduction and motivation on why we did this. And then I'll talk about the dynamics model we used to like simulate like an AUV. We are using an Unreal Engine-based environment in the background for the visualization, so I'll talk a little bit about that. I'll also touch on some of the future work we have planned, and as Alicia mentioned, we do have a MathWorks award for RoboSub, RobotX, and SUAS. So I'm going to talk a little bit about how that would look like this year for RoboSub, and then at the end we'll leave some time for questions. So for the motivation part, like I said, MathWorks has this environment that was built to allow students to simulate the dynamics of an AUV and also let the teams test their solutions in simulation before they get into the water. So oftentimes, software teams are often waiting for the hardware team to get their AUV done so that they can go ahead and test. So this is something that they can do in simulation to get their software working in parallel and then hopefully reduce the development time for the competition. And we also are planning to host like a virtual RoboSub competition. This is again part of the MathWorks award. So last year, if you remember, we had just an award for award that basically scores you on how you use Simulink and MATLAB for your AUV design. This year we're going to do something very similar to RoboSub, but in a virtual environment, so that this would give you some time to like run your algorithms and your navigation in simulation, so that when you come to RoboSub, you'll be better prepared, and a lot more of you can qualify and get to the finals. And of course, we give out $1,000 to the winning team, so there's also a monetary aspect to it. But I'll talk a little bit more towards the end about this competition. And then finally, we also thought this would be a good use for researchers and professors who are doing marine engineering and have like a generic underwater environment. Right. So these are the requirements that we kind of worked with. It's a very high level, but what we wanted was realistic underwater environment because, as you know, RoboSub has a lot of vision-based task solving. So the underwater environment needs to look good so that you can use that data, the visual data in simulation, and then deploy it in the real world. And then obviously we need support for some frequently used sensors like IMU, DVL, cameras, pressure sensors, etc. We also need the dynamics with some varying complexity. So by varying complexity, what I mean is some teams do a lot of work on their AUV and they also do a lot of analysis. So they get the coefficients, they do CFTs, they get coefficients of drag. So we want to be able to import those coefficients into Simulink so that you can get a much better fidelity in simulation. But for those who don't have time to do all that or have not got to that stage yet, you can always go with a simpler model. So you give a simpler drag coefficients to like approximate the AV dynamics to like a really good extent. And then I'll talk about how that looks like when I get to the dynamics part of it. And we also wanted to support some actuators like torpedoes and droppers, which are again very common in RoboSub and something that a lot of teams struggle with, especially station keeping and trying to have the AUV shoot the torpedo correctly. So this is the quick view of the environment. Right now the pool is pretty sparse. You see only like a few objects in there. So there's this navigation gate. And then there's a torpedo board. Right now, it's pretty sparse because we will update it once we get. Oops, sorry. Let me go back. Yeah, we'll update it once the task details have been released, and then you'll have whatever task that has been planned for this year's RoboSub in this environment. Uh, Yeah, and then of course, what tasks can you actually do in this simulation environment? We could do the navigation gate. This is based off of these pictures are based from last year's competition. This will be updated for this year. I saw the images were released, so I'll update them once I get a chance. And we'll also have like buoys, so you could do the slalom, and we have torpedo boats for you to practice torpedo firing. We also have the marker dropper task and the octagon surface. We don't currently support any of the finger tasks. So right now that is still something that we are considering and trying to figure out how to fit it into this environment. But hopefully we'll have that in the future or in the next iteration. Now I'll quickly talk a little bit about the environment. So the Unreal environment was modeled using the water plugin that comes with Unreal Engine. It's an experimental plugin. And then the underwater look was achieved with some custom post-processing block to kind of match what we found in the real data that teams have uploaded to the RoboNation box. So if you see here, that is an image from underwater taken from one of the AUVs, and then this is the simulation environment. The floor texture has not been updated yet, but you can see like the fog that is there. Like the distance looks a little blurry than whatever is nearby. And then there's also some caustics, which causes some issues when you're trying to detect stuff under on the floor, especially when it's bright and sunny. So we added that. Um, it's not real-time caustics, so you don't have to worry about GPU usage. It's just a pattern that's being projected on the floor. And this is also something that can be turned on and off so that you can, collect images without these and then add collect images with the caustics to get like more variety in your data. So now I'll switch to Simulink and then show you the dynamics model and some of the tasks demo that we have. We open MATLAB. So this is the Simulink model that um, that's responsible for the environment. Actually, before I show what's inside this, I want to let you know that all these files that I'm working on is available on GitHub under MathWorks Robotics RoboSub Virtual Environment. It's also available. This link is also in the video description, so you can click on that to see to like go here. You can clone it and work on it. Another detail is that this is open source, so you can contribute to this branch to this model. You can do your own work, raise pull requests, and then we review it and then add it. So if someone wants to add a different sensor or wants to they have an idea for the underwater finger task, you can make your own developments and then add it to the and then raise the PR and then we'll approve it once it goes through our verification process. All right, let me go back to Simulink. Yeah, high level, this is what the model looks like. Basically, you have a mask subsystem. What that means is there's a bunch of blocks inside this big blue box, but then we give the mask gives you like an interface to interface with all the parameters inside this box. So if I open this, if you just double click on this, you'll see it has all these parameters that you can enter. And these are like generic parameters for your AUV, like um, we support like STL files so that you can have your AUV body in the simulation. What's your center of buoyancy? What's the height or diameter of your AUV? What's the volume, inertia, mass, and all such details? And also the thruster position. So if you have like six thrusters, how are each of them located with respect to the center body of your AUV? So if you have six, then I would have like posts for each of them. And then you can also choose what kind of battery you're using. So we have like 10 to 20 volt. And then you just let us know what number of thrusters you're using. Right now, these thruster values are modeled based on the T200s. We will be adding more support for like T500s and T100s in the future. But since T200 was the most common one, that's what we started with. And then if you click on hydrodynamics, this is where I mentioned where you have like different fidelity for your simulation. So this is the simple one where there's a linear drag coefficient and a quadratic drag coefficients. So this one acts when the AUV is moving at low speeds, and then the quadratic drag acts when the AUV is moving at high speeds. And then we also have like an angular damping coefficient. So these can be tuned to your system. I'll talk a little bit of how you can do that when I run this model, but this is how you do like simple hydrodynamics. If you want to do complex, what that does is importing your coefficients from any CFD software that you've used. What we're doing is getting the roll, pitch, yaw, normal, all these coefficients in a separate axis, and then doing a more involved hydrodynamics for this to take effect. So you see more realistic movement. But if you start with simple, you still get a pretty close approximate. This is useful when you see like some peculiar behavior that you don't see in simulation, but it happens in real life. It's probably because um, some of these coefficients are creating some kind of a force or a moment to make that AUV spin or move in an undecided direction. So if you have a more complete estimate of your coefficients, then you could use the complex, but you could always start out with a simple hydrodynamic simulation. So these are the AUV parameters, and then there are sensors. Right now we have two cameras, DVL and IMU. So for the camera, I have one that's facing downwards and then one that's facing forward. You can set these parameters of your camera based on what camera you're actually using so that um, you can match the real sensor, and you can also output depth from your camera. so to like simulate the depth data. Outputting semantic segmentation doesn't work right now, but then I'll be making some updates to make that work as well. So that way you can get ground truth data for the data that you collect. Forward camera is the same thing. It has the same exact parameters. It's just not rotated. So if you see downward camera, it's pitched down by 90 degrees to face downwards, and upward is just 0. And then we have the DVL. It has two modes, water tracking and bottom tracking. And then we have the IMU, which has a bunch of values that you can put. These are values that you get from the IMU datasheet. So this is again to model realistic noise from whatever IMU that you're using for your AUV. So you can just go to the datasheet, pick up these values, and then put it here to get a more realistic idea of what kind of noise you can expect from these IMU. Yeah, so you can do that for the accelerometer, gyroscope, and magnetometer if you have a 9-axis IMU. And then, like I said, we have two actuators, a torpedo and a marker. This is basically where the torpedo is located in your AUV. So the location where you have the torpedo mechanism at. And then some environment constants like water density, acceleration, if you want water current or not, and do you want to enable water caustics. So I'm going to check enable right now and apply it. Before I go in and show what's inside, I'll just quickly run this demo to show you how the environment looks. I'm going to change this to infinity so that it doesn't stop halfway. Right. This is the environment right now. You can see I have an AUV model here that's it's positively buoyant, so you can see it just floats up. But you can see the gate, the torpedo board over here, and then there's a marker board right over here. And then these images will be updated later. Oh, and of course there's like an octagon right here for you to surface. And then you can see here, this is like the marker that we have. And then this is the torpedo that was fired. This is, I know this is like the bare bones of the environment. You can always add more stuff. You can import files from Blender into this environment and then place it wherever you want. You can modify it like that. I'll talk a little bit about how you can do that in actually the next step. I'm gonna stop this model right now, and then I'll go inside the mask subsystem. Oh wait, before I go inside, I also have to talk about the inputs to the subsystem. So you have thruster PWMs that would be the input. So if you have 6 thrusters, you need an array of 6 values for your PWMs. So here I have a 6x1 double. And then you need a fire command for the torpedo and the marker. So that'll just be a step signal, really. Just changes from 0 to 1 to fire that system. Now to go inside, you can click on this little arrow you see here, or you could also do Shift U. I'm just going to click here, and this is what's inside that main subsystem. So you have the dynamics, you have sensor modeling, you have the actuators, and then you have some visualization. So I'm going to quickly start with visualization because I want to touch on how we can import meshes into the simulation. So for example, if you want to add some image from your Blender and let's say you export the image or like the object from Blender as an FBX file, you can go, um, actually, hold on. Let me just create something to show you. you just search for Simulink 3D actor, you can open that and then set the path to that source file, to like that FBX file. And then in the transforms, you set the XYZ and roll pitch yaw, and then the scale, just to make sure you guys are aware of this. Unreal units are centimeters, and then so a lot of times when you export from Blender, it's usually meters. So when it comes here, it might be blown up. So make sure either the scale in Blender is set to centimeters, or when you get it here, you scale down by a value of 100. Yeah, so you can add or any of the objects from Blender into this environment by just getting in a simulation 3D actor and then setting the source, setting the path to the FBX file you exported. I'm gonna delete that. And then the dynamics is what does all the physics of the AUV. So you have environmental forces and moments block that calculates forces and moments due to hydrostatics and hydrodynamics. So if I go inside, you can see there's a hydrostatic block, which just calculates your force due to gravity and then buoyancy. And then you have hydrodynamics, which takes in the speed and then multiplies it with your linear and quadratic coefficients. This is for the simple system. And then this is the more complex system, which basically takes in all the constants and then simulates the aerodynamic forces and moments. Those are the environment forces. And then we also calculate the forces due to the thrusters. So based on the PWMs and the location and the orientation of these thrusters, this calculates the total force and the total moment from your thrusters, which then gets added with the environmental forces and moments, which are then fed into the 6DOF solver, which basically takes in the forces and moments and then solves the differential equation to get you a velocity, position, and all the robot states for the next time step. And then it does it every time step. Here, for this model, the time step is set to 10 milliseconds, so it runs 100 times each second. But if you want higher fidelity, you can also reduce the time step to maybe 5 milliseconds or even 1 millisecond. Yeah, so you get all of these states right here. So if we zoom in, you can see velocity, position, Euler angles, quaternions, rotation matrix, and the velocities, and then you calculate acceleration, which then is your entire robot state. And then what the sensor block does is take this robot state and then basically add in some noise. So for example, the IMU just adds in noise, whatever that was added in the mask that I showed in the first page. And then outputs this noisy values to your sensor bus. And then DVL does that. Right now, what I have for the DVL is a file that just takes in the speed and the depth and then adds some noise and then outputs it. So it is not a high fidelity simulation of a DVL. It's more of a workaround to get some kind of a DVL output. But again, this is something that we are working on to get a better model for. And of course, the cameras produce the images that also go into this sensor bus. And then finally, the actuators. Uh, the two actuators are very similar. For example, the torpedo takes in the robot state, and what it does is samples it to get the current robot's position at the time of firing, so that it can, whatever physics is done to the torpedo block. For example, if you're calculating the new position once it has been fired, it's just added to the position the AUV was at when it was firing, so that it moves in the right direction and right velocity. So that's basically what this does. It has a trigger subsystem which then gets the initial state when it was fired, And then we do the same thing. We get the environmental forces and moments acting on that torpedo, and then update the torpedo states, which then goes into the visualization environment. That is the same thing for the marker dynamics as well. For the marker, it's a little more easier because I'm assuming the marker is very heavy, and so the main force acting on it is the gravitational force, and there's not a lot of buoyancy. So it's much more simpler to do the dynamics for the marker. And then you get a marker position, which then goes into the visualization block. So you have the torpedo, the marker, and the robot going into visualization, which then does all the visualization for you guys to look at. So that's the gist of the environment. You can find actually more details if you go here. There's like a PDF. It's loading. So there's like a PDF that has a lot of details on each of these. So it talks a little bit about the coordinate systems used, all the mass parameters that I just mentioned, some sensors, actuators, and how the dynamics is done for all these blocks. So this is a little bit more in detail. And it also links to a lot of MathWorks documentation pages if you want to know how certain blocks work or how certain blocks respond. You can also check that from through the links in this document. And of course, if you still have any questions, you can reach out to me on Discord, or you can also email roboticsarena@mathworks.com, and we'll get back to you and try to fix it as soon as possible. Right. Before I go to the task, Alicia, are there any questions?
Yes, we actually have a few questions. One of our attendees noted that they didn't do any of the work last year for the RoboSub award, so they're noting that they're curious to do that for their team. So that's very exciting. But another one of our questions that we have is what is the best way to tune PID controllers using this model?
Okay, so I'm actually going to show you that in the next section. I'm going to talk about, I'm going to simulate some of the tasks, and I have like a simple PID to control the AUV. So I'll quickly talk about that in the next section, but hold on to that.
Great, great. We will hold on to that question. A couple more quick questions. So one of them was, so our software team will have the ability to customize it further than the base model you've created. So the simulation.
Yes. Yeah.
Great.
So you can add in more files from Blender, and the Unreal environment itself uh, will be also open source. So you can go in and then change, like if you don't want a pool, you can change it into like a Transtick environment or something else as well. So you'll have like full ability to change anything that you want in this environment.
It's amazing, amazing. And I know you've added the graphics from last year into it, and you said you'll be adding the updated graphics
Yeah.
for this competition. So
Mhm.
thank you so much for doing that. And then, like you said, you'll be able to do a little more customization. And then the final question we have right now is on, I think a couple screens ago when you had velocity E and velocity B, and they asked, what is the difference between velocity E and velocity B?
Right. So velocity E and B are like the velocities in different coordinate systems. The net coordinate system is velocity E, and velocity B is like body coordinates. So, for example, if you have like the AUV, my background is not letting me show the object. Okay, assume this is the AUV, and if it's moving forward, this is forward X for the body, for the AUV body. But if the net, for example, if the net coordinate system is also X in this direction, they all line up, and velocity B and velocity E would be same. But if the AUV is rotated, then your velocity B would actually be Y of velocity E because it's rotated 90 degrees in yaw. So that's basically what it means. It's just velocities in different coordinate systems. Based on what you use for your development, you can either use velocity in the body axis, or you can use velocity in the net axis. And again, that's explained along with the coordinate systems in the PDF that is in the GitHub. So you can always get more information there.
Great. Thank you so much, Abhishek.
Mhm. All right. So I will now go to the next model that, as one of the questions was on PIDs, I'll go to this model and then show um, how I did a simple PID for this robot. Media viewer. All right. So here you can see the AUV block that was there last time, but then instead of like having constant blocks that is feeding into it, we have a planning and control block that would give a cluster PWM values and torpedo command. And if you go inside here, what it does is it's a simple state machine that tells the robot where to go, and then there are different PIDs to simulate to like control the robot to make sure it you know it stays on the path that the mission plan is sending it. So how this works is in here I have some states. So initially I tell it to dive to a certain depth, and then it's going to move forward to the navigation gate and then move to the location based on these values to go to the torpedo task. And then it's going to go there and then stabilize for a few seconds and then fire the torpedo. And then it's going to surface. So that's like the flow of this logic. So it's going to dive, go through the gate, fire the torpedo, and then surface. And once you have these reference positions, so of course, right here, I am using my knowledge of the simulation environment to give it direct positions of where it needs to go. When you do it in simulation or when you do it in the competition, you don't have the direct information. You need to rely on sensor values. Right? You need to check on your camera, check where the target board is, and also do some kind of state estimation, make sure you're where you think you are, and all that stuff. But I am not doing all that. This is just a simple example to show if you know where to go, how can you like set up a few PIDs to achieve that. Here I have like three PIDs for X, Y, and Z. Um, and then I have some constants here. This was tuned based on simulation, so I would run it, see how the system performs, and then tune it based off of the performance. And then I also have some saturation because the thruster cannot put in more than this number of this Newton of force into the AUV. For example, I have two thrusters facing forward, and each T200 thruster can output around 5.2 uh, kilogram force, right? And then it's around -4 in the negative direction. So I add these so that the PID doesn't, tell it to do like 1,000 units of thrust. And then have some anti-wind up so that the saturation doesn't affect the PID loop. Um, and this is just a basic PID block from Simulink. And then I'm again just going in and then dividing it by two because I have two thrusters, and then I have a lookup table that basically calculates the required PWM for whatever thrust the PID is telling it to output. And once I have that, I'm going to send all of that into thruster PWM, and then the torpedo command would go here. So before I show you how the tuning was done, I'll just quickly show you the model itself and how it runs. So that is the camera. Then if I go here, you can see that it is moving forward. Actually, hold on, let me pause this. I am gonna show you with respect to the planning part. So you can see that it is currently in the navigation stage. I mean, in the navigate stage in the mission plan. So I'm going to continue, and then you can see that it's going into the nav gate. There's also the camera view, but I am going to minimize it so that I can focus on the environment. And then once it has gone, it's going to dive down again because it's in the torpedo dive stage. And then it's going to move in the X. X is like right here. And then it's going to move forward again till it gets close to the torpedo boat. So once it's nearby, it's going to stabilize for a couple of seconds and then fire the torpedo. So you can see the torpedo fired, and then the torpedo just floats up, and then it's going to surface once it's done with its mission. So that's the model. Again, like I said, navigation part was made super simple here because I already know where the AUV has to go. And then I'm using simplified hydrodynamics. So some of the movements doesn't create any quirky, AUV twists or turns. But that just shows you how this can be done simply. And then for the PID tuning itself, what I did was, so right now if I open this code, you can see the errors. I am gonna reset it so that it's new. Okay, so you can see the X, Y, and Z error, and then you can see that every time I give a new command, the error goes up and then settles back to 0. So this happens in all these axes. It goes up, come back to 0, and then it keeps happening really. And then in some cases you see like overshoot, and you see that it takes a lot of time for it to go. And so these are depends on your system requirements. So like what's the maximum speed you can go in, and what's the maximum force. And if it's positively buoyant, then there's going to be a lot of force pushing it up already. So if you have if you set a Z reference that is higher than the robot, then it's going to be pushed up pretty soon. So there might be some overshoot before it settles at the reference value. Um, And then for tuning itself, what I would recommend is you go inside here, and then you basically comment out the visualization part, right? Because for tuning, how the AV responds, you don't need all the visualization. So I'm just going to comment that out. Just make sure that if you comment out the visualization, you also need to comment out the camera, because without the visualization part, the camera is really not going to see anything and it'll throw an error. So now you can go in here, and then let me just show, for example, I delete these two and just show how the Z performs. And I'll give it 30 seconds to run. If I run it, yeah, the model ran pretty quickly because without visualization, it's really fast. Then you just open, you can see that this was the error. Let me actually zoom in so that you can see. For now, don't mind the blue and yellow lines. I deleted those, but you can see that the error goes up, and then there's like a little undershoot before it, settles back. So you can work on that. For example, I can go in here and then reduce the p-value maybe and make it like 75. And then you can see that the undershoot is maybe 18 into 10 power minus 3. So let's see, with 75, it gets lower than that. Again, really, this undershoot is totally fine in a lot of cases, but if you want really strict control, you can always tune it. So I'm going to run it again with a new p-value. And actually, it overshoot more than what it did before. So I'm going to go back and then change it to 120. increase it a little bit. Yeah, and now you can see that the overshoot is considerably less. So it all depends on your design parameters and what you want to do. But yeah, that's how you would typically tune like PID for the controller. So right now I'm doing more of a position control, but if you want to do, oh, sorry, if you want to do velocity control, you could do that as well. So instead of taking the robot's position value from the robot state, you would be subscribing to the robot's velocity or the robot's, acceleration or body velocity. And you just click on this plus, and that would be a new input in this bus selector. So that way you could do like velocity control if you want to do, for example, a joystick control. You could tune it with this as well. But yeah, that's how tasks can be executed. And of course, this is all in Simulink. But if you already have, I know a lot of students use ROS2 a lot, which is great. So if you want to use ROS2 with this simulation environment, it's actually pretty easy to do so. What you would do is just go in. So you need to like publish the sensor values and then subscribe to. So instead of this planning and control, this will be coming in from your ROS code, right? So you need to subscribe to thruster PWM and torpedo command. So that you could do by just searching for ROS to subscribe, and then that would be like a subscriber block that you get. And then you just if you already have a ROS2 network running, you can just select from a ROS network. Right now I don't have anything running, so I just have the basic ROS topics. But if you have something, then all those topics would show up. I've talked a little bit about this in my previous webinars, so I would suggest looking into those with RoboNation. Um, and then, yeah, so what you would do is subscribe to the topic that you're publishing with Trusted PWM Sins, and then that would go in here. So instead of this, you'll be sending the message directly into your simulation. And then the same for publishers as well. So if you want to publish, for example, the IMU data or the image data, um, what you would do is ask to publish. And let's say you have the image somewhere in this bus. There's like a ROS image writer, I think. Yeah, that's the image writer for ROS2, and then you just pass that image into this, and then the message into this, and then choose the topic, the same thing, and then you would be publishing your simulation, the images from your simulation to the ROS network, which you can then subscribe to from your ROS machine. All right. Yeah, so that's how the the dynamics works, and then how we can tune controllers or test out basic navigation and see if the robot behaves like you want it to. The other thing that I want to talk to is also tuning these values. So for example, hydrodynamic coefficients, these values really depend on your AUV. So for example, if your AUV is positively buoyant, right, and then you place it at a depth of 1 meter below the pool, you can see how long it takes for the AUV to like surface up, and then use that to determine the drag coefficients. So this is the 30 is the drag coefficient in X, 22 is in Y, and then 220 is in Z. So for me, in X, it's going to be very small because of the shape of my AUB. It's more what's the word for it? It's more optimized, I guess. And then when it goes up, there's more surface area, so there's going to be more drag when it's going up or down. And then you can change it and then simulate the system to see if it matches your real AUV's performance. And once you have a close enough estimate, you should be pretty good to continue with your simulation environment. Aerodynamic, that's the word. It's more aerodynamic in the x direction, so it doesn't, it has lower drag. But yeah, I'll go back to the presentation. So for the dynamics results, like I said, for a positively buoyant system, this is how it would behave. You can see that this takes about um, what maybe like 1.7 seconds to get to the top of the water. This could be pretty fast. Maybe your AV doesn't go up so fast, so then you would change that drag coefficient to reflect what happens with your AV. And then you can also see, you can also do that in different axes. You can give a like a constant positive velocity in the x direction, like surge velocity, and then see or like constant thrust values in the surge direction, and then see when the velocity stabilizes. So initially it's going to accelerate to a value, and then the force from the thruster is going to match the drag force, and then it's going to stabilize at a constant velocity. So you can see how long that takes for the velocity um, to like come to a stable value, and you can use that to tune your drag coefficients, linear and quadratic drag coefficients. And you can do the same thing in y and yaw and all the different axes as well. And here you can see the roll stability. For example, if your center of buoyancy is above center of mass, if there is a roll moment, it's going to stabilize back because of the difference in the buoyancy and mass. And again, if it's offset in the y-axis, you'll see the robot basically flip because now mass and buoyancy are acting with some radial distance, which would then cause a moment about the x-axis. So this is just some test examples that I chose. Again, you can do some more tests, make sure your AUV performs like how you think it would perform in the water, or like how you it actually performs in the water to match the simulation with the actual AUV. Now that I've showed you what is here, I'm going to talk a little bit about some of the future work that we have planned. Right now, collision is not great. Actually, collision is non-existent in the model. It would basically just go through the walls if you collide with the walls of the pool. This is because the unreal physics kind of messes up with the Simulink physics. So there are some issues with the collision, which is why it's turned off for now. But once we have that figured out, we will update it so that there's better contact and collision modeling for these objects. And then, of course, we want higher fidelity sensors like for the DVL, and maybe more sensors as well, like, FOGs, which is something OSU was working on, things like that. And then we wanted to support acoustic tasks and then increase number of torpedoes to 2. And then also improve the pool flow texture. Right now it's pretty blank, so we'll improve that texture. And then have some automated scoring. So if you do a run in simulation, then you would get like some kind of a score based on how the AUV performs. And the other one was like have an additional environment for TransTech if and when we go to TransTech, so that you can use that to simulate the AUV. And then there are also one more thing that I forgot to mention is that right now this system works only in Windows. We are working on a Linux executable that also works on Ubuntu. So hopefully it should be out soon, but I cannot make promises because we have some other issues going on. But hopefully it'll be soon and ideally this month. Yeah, and finally, I want to talk about the MathWorks Award. Alicia, how much time do we have? And I did not check time at all.
So you are good. We still have some time and we can go over a little bit if you've got time still. But we've got about 10 minutes or so left and then a few questions to answer. But you've been answering the questions along the way without realizing.
Mhm.
This is perfect.
Okay, that's great. Um, so yeah, back to the MathWorks Award. Last year we had a lot of good submissions. Um, for the award for RoboSub, and shout out to ETS Montreal for winning the award last year. But this year we're gonna try to do like a virtual competition with the task being very similar to RoboSub, which would then give the teams a chance to like test their solutions in simulation and be better prepared for the actual competition. To reiterate, this is only for the students who have already registered for RoboSub. You can use the environment otherwise. If you're not registered for RoboSub, you can use it for your own personal research, but you will not be eligible for the competition or the MathWorks Award. So the prize is worth up to 2,000. The winning teams gets $1,000, and then 750 for the second and 250 for the third, I believe. And we will have more details out. We'll work with RoboNation and send out more details once we have finalized the environments. But that's it. If you guys have any questions, I'd be happy to take them. But you could also email them to roboticsarena@mathworks.com or reach out to me in Discord if you're part of the RoboNation Discord.
Fantastic. Thank you so much, Abhishek. Like Abhishek mentioned, the award he just spoke about is specifically for students that are registered for RoboSub, but registration is still open. We have till April 1st. So for those of you that are curious what RoboSub is, make sure to visit robosub.org to learn more about it, or feel free to reach out to competitions@robonation.org, which we'll throw into the chat, and you can learn more about the RoboSub competition there. Before you head out, I'll ask a few of these questions. I know you just touched on some of them.
Mhm.
And then, like Abhishek mentioned, if you've got more questions about the specific environment, please feel free to reach out to him. I know you just touched on it. One of our questions was about if this is, he said the link only gives a Windows executable, so will you be able to provide a Linux executable for
Yeah,
using on Ubuntu, which you just discussed?
we
Um,
will we will be doing that. So we have been swamped with some kind of other work right now, but we will be compiling a Linux executable and also open sourcing the Unreal editor itself so that you can compile it yourself in the future if you want to make any changes, and you don't have to depend on us for that.
Fantastic. Our next question was, can the simulation be used for hardware in the loop simulation? Can we have this simulation running on a lab machine and have the control and autonomy code running off device on the actual AUV hardware?
You could do that. It might be a little more involved. You'll have to set up more stuff, but it's definitely possible. You can. It also depends on what you're using to communicate. If it's ROS, it's like I showed you, it's pretty easy to do it. But if you're using some other modes, then we can definitely work on it. So send me more details on what your setup looks like, and then I can work with you guys to get that up and running.
Fantastic. Alex, if you missed that, make sure you reach out to Abhishek with some more questions about that specific query. We've got another question, which is this the same signal? So the signal that you were, I think, discussing a little bit earlier, that our real ESCs are receiving, and does the simulator include thruster response delay?
We don't have a response delay right now. Right now, it just takes in PWM values and then provides just as soon as those values are being received. But if that is something that's important, we can try. You can also add that as an issue to GitHub, see if, and then we can try to work on that in the future as well.
So, and then we had a little bit of a discussion in the chat about FSMs, finite state machines. So is this
Right.
implementing a finite state machine or something closer to a behavior tree?
The state flow chart that I showed you, let me switch back to that one. This is a finite state machine. So it's just going from one state to another. The statement inside, like the square brackets, are the conditions for it to change states, and then the ones inside the curly brackets are the output from once it does that transition. And this is also a really nice way to develop state machines because you can like add breakpoints here. So if your state doesn't change from one to another, you can set a breakpoint and see why it's not happening. And you can also generate C code out of it. So once you're done developing, you can deploy it as a C++ ROS node or just like a library that you can link it to your existing project. But yeah, these are state machines.
Fantastic. One of our questions in that discussion about the
Mhm.
state machines was they were interested to hear whether the architecture is meant to stay FSM based as teams scale up missions or if there's flexibility to support other approaches.
If you're using Simulink, we don't support behavior trees. If that's what you want to use, we only support state flows and FSMs. But if you want to use behavior tree, you can always, build it in your, if you already have one running, you can just, output those as ROS topics and subscribe to them here. But right now we do not support um, behavior trees.
Great. Thank you for answering that question. And then our last question that we had for today's webinar is, are the competition elements such as the gate, octagon, torpedo, and task panel fixed in the 3D space of the simulator, or does their pose estimate update too?
Right now, they are fixed in the simulation environment. You can modify them to like, move it, to turn it around if you want. But once the simulation starts, wherever you place them, they would be fixed in it, so that you don't see the sway of those objects that you would typically see in a real world environment. Uh, we tried to model that, but just turned out to be a lot of physics and slowed down the system by quite a lot. So for now, we just don't support physics for those objects.
Great. Thank you so much for answering all these questions. We got a bunch of thank yous as well in the chat. So thank you so much. And again, this is a big shout out to Abhishek here. He pulled this together and did this for each and every one of you guys that's in the comments, and also those of you who are listening, and those of you who will listen when you see this webinar at a later time. But it's going to be such a wonderful addition to the RoboSub community. So please send your big thank yous in the chat or the comments, or feel free to email and reach out to Abhishek directly and say thank you for pulling this together for RoboSub.
Yeah, thank you all. And
Awesome.
thank you, Alicia, for organizing this webinar.
Absolutely. Like Abhishek mentioned, please feel free to reach out if you've got questions. If you've got questions for RoboNation about the RoboSub competition or any of our other programs, feel free to reach out to competitions@robonation.org and visit robosub.org as well. But thank you so much, and we look forward to seeing you guys next month for our next MathWorks mini-series session. We'll be sending out a bunch of emails and posting on Discord and over our various social media channels to promote that. But we'll see you guys next time. Thank you.
Thank you.